So how do scientists actually talk about the distance to a galaxy or the size of an atom without having to write out a page full of zeros? Well, today we're going to decode the secret language that makes it all possible. We're talking about prefixes and standard form.
Here's our game plan. First, we'll look at why writing out super long numbers is a huge problem. Then we'll check out the two really slick solutions scientists use, prefixes and standard form. After that, we'll put them to the test with a real calculation. And finally, we'll get into why in science, the right answer is about so much more than just the number itself.
Okay, let's dive right in. To really get why we need these tools, we have to talk about a massive problem in science. And that problem is zeros. Just so many zeros. You know, science deals with numbers that are so incredibly huge or so mind-bogglingly small that our normal way of writing them just doesn't cut it. Let's just take a simple example to see what I mean. 1 billion joules. It's a lot of energy, for sure. But just think about it. How would you actually write that down on a piece of paper? You end up with this. A 1 followed by 9 zeros. I mean, it's long, it's super clunky, and honestly, it's a total recipe for disaster. It is so easy to miscount those zeros, and in a real scientific calculation, that could be the difference between a rocket reaching orbit and, well, a very expensive firework. There has to be a better way.
And thankfully, there is. The first tool in our mental toolkit is a special kind of shorthand, a set of prefixes that scientists all over the world agree on to make these gigantic and tiny numbers manageable. Think of it like a secret vocabulary just for scale.
Now, this table might look like a lot to memorize, but here's the trick, the way to remember it. Look at the pattern. Notice how the powers of 10 jump in threes. You go from kilo, which is 10 to the 3, up to mega, 10 to the 6, then giga, 10 to the 9. And it works going down into the small numbers too, milli, micro, nano. Learning them in these groups of 3 makes it way, way easier to remember.
And here is just a brilliant little memory hack to lock in one of the trickiest ones. Nano kind of sounds like non, which is the number 9 in some languages. It's a super simple way to remember that nano means 10 to the power of -9. Simple, right? But so effective. Now, you know how there's always an exception to the rule. Well, here it is, and this one is a big deal in physics. For almost every other measurement, the base unit is just the plain unit, no prefix. But for mass, the standard unit, the one you have to use in equations, is the kilogram, not the gram. It's really the one time a prefix is part of the standard, so just burn that one into your memory.
Prefixes are fantastic, but they only cover specific steps, like thousands, millions, billions. What about all the numbers in between? For that, we need the universal key, the master tool that can handle absolutely any number you can imagine, and that is standard form.
I mean, you can just see how much better this is. On the left, you've got a total mess of zeros. On the right, it's clean, it's simple, it's elegant. That 1 billion joules just becomes 1 times 10 to the power of 9. A millionth of a joule, 1 times 10 to the -6. It's so much clearer and way harder to mess up.
So what is it really? Well, it's just a system, a set of rules. You take any number and you rewrite it so there's only one digit that isn't 0 in front of the decimal point. Then you just multiply it by 10 to whatever power you need to get back to the original number. It's a consistent language for every single number.
Okay, so sometimes your calculator might give you an answer like this, 720 times 10 to the -9. It's not quite proper standard form. Remember the rule. We want just one digit before the decimal. So we change 720 to 7.20. Simple enough. But wait, we moved the decimal 2 places to the left, which made the number smaller. To balance it out, we have to make the power bigger by 2. So -9 plus 2 gives us -7. Our final proper answer is 7.20 times 10 to the -7.
All right, enough theory. Let's get our hands dirty and see how all this stuff actually works in practice. We're going to use these tools to solve a pretty common physics problem about waves. We're going to be using this classic little equation right here. Wave speed equals frequency times wavelength. It looks like a simple multiplication, but as you're about to see, there's a small twist. Okay, so here are the numbers for our wave. We've got a frequency of 5.3 gigahertz and a wavelength of 720 nanometers. And you should immediately see the trap, right? We can't just multiply 5.3 by 720. We've got these pesky prefixes, giga and nano, and they represent huge differences in scale that we absolutely have to deal with.
And this is where our whole system just clicks into place. Step 1 is always to convert. We swap out the prefixes for what they really mean in standard form. So 5.3 gigahertz becomes 5.3 times 10 to the 9 hertz, and 720 nanometers becomes 720 times 10 to the minus 9 meters. Now that everything's in the same base language, we can just plug them into the equation and let the calculator do the hard part.
So we punch those numbers in, and boom, we get an answer, 38016 meters per second. Great, that's the speed of our wave. We're done, right? Well, not quite. There is one more absolutely critical step we have to take.
And this last part brings us to a really deep idea, something that separates okay science from great science. You see, an answer isn't just about getting the right digits. It's about understanding how much you can actually trust those digits. It all comes down to precision. So let's look back at the numbers we started with. Our frequency was 5.3 gigahertz. That has 2 digits that we're confident in, so we say it has 2 significant figures. Our wavelength was 720 nanometers. That has 3 significant figures, the 7, the 2, and that final 0 is also counted. What this tells us is that our 2 measurements were made with different levels of precision.
And here it is. This is the golden rule of doing calculations in science. You have to remember this. Think of it like a chain. A chain is only as strong as its weakest link. In the same way, you can't magically create precision in a calculation. Your final answer can only be as trustworthy as your least trustworthy measurement.
So since our least precise measurement, the frequency, only had 2 significant figures, our final answer can only have 2 significant figures. That means our raw calculator answer of 3816 has to be rounded. We keep the 3 and the 8, and the rest become placeholders. So the scientifically correct answer is 3,800 meters per second, because that number accurately reflects the precision of the data we started with.
And that leaves us with this final thought to chew on. How much of science is really about finding an answer, and how much of it is about knowing exactly how much you can trust that answer? When you master things like prefixes and standard form, you're not just learning how to make calculations easier, you're learning the very heart of the scientific method, understanding not just what we know, but how well we actually know it.